Hey power electronics enthusiasts and engineers. Are you working on renewable energy projects but finding it tough to design on-grid inverter that's highly efficient with straight grid codes? The heart of any modern solar on wind energy system is the digital control. Getting it right is a major engineering challenge, from maximizing power output using maximum power point tracking (MPPT) to ensuring safety with fault right-through (FRT) and anti-islanding protection. Power electronics devices are the essential part of modern power systems, but the challenges are inevitable. For example, maintaining grid synchronization, ensuring high power quality, and achieving stable operation during faults. That's why accurate component level modeling is non-negotiable. Here we are opening up the complete simulink model for three-phase on-grid inverter, breaking it down pieces by piece. I will show you exactly how to model the critical hardware and implement the control logic. You are going to discover how to design the core power state featuring the IGBT-based inverter and master the control system, including the voltage regulator with its precise PI controller and the PWM generator. Ensure clean power injection using realistic line inductance and capacitance simulation. The LCL filter components connect to the utility system using a three-phase two-winding transformer and accurately simulate the external grid environment, and implement the crucial phase locked loop PLL, as you know, for seamless synchronization. We also have the simulation of the real-world conditions with components like the circuit breaker and the specific load models. Finally, we will analyze performance by measuring the essential metrics: grid and inverter voltage, current, and the critical active and reactive power being injected into the system. If you are serious about mastering complex power electronics, subscribe now and let's jump straight into the details. Now we are heading to the simulation part, and in this video I will show you the power circuit of our simulation. First, we add two DC voltage sources with the value of 500 volts for each. Then we add the electrical reference here. And don't forget to add the solver configuration. Don't forget to add the solver. And the solver for the equation formulation is time. Index reduction method should be set to derivative replacement. And consistency tolerance should be 10 to the power of minus 9. And for sample time here in the simulation, 10 to the power of minus 6 has been chosen. Then we add the inverter. So we have the three-phase inverter here, and change the configuration to the expanded three-phase ports. And for the switching device, choose the IGBT one. And as it was explained in the introduction part, the LCL filter will be added to our line. And here we have the inductance section with the value of 3 millihenry.
Now we add the capacitance characteristic of the line. Then for the rated voltage, set it to 380 volts. Rated electric frequency, it depends on the frequency that you have chosen, 50 or 60. And for the capacitive reactive power, 3000 volt ampere is recommended. Then for the measurement at the current and voltage sensor, again also change this one to the expanded three-phase port. Connect to the lines one by one. This measurement is for the inverter side, as you can see in this diagram. We also add voltage sensor for the face-to-face measurement of our lines. Later on we will need it in our calculations. Then connect the outputs to the PS simulink converter. Later on we are going to connect them to our scopes and see the results. Again, another load will be added. This time the component structure is resistance. Rated voltage is 380, and for the real power, 50 kW is designated for this element. And don't forget connecting all those necessary elements to the electrical reference. Now it's time to add the circuit breaker. And the modeling option can be expanded three-phase ports, PS control port. And for the closed resistance, 1 milliohm is set. For the open conductance, 10 to the power of minus 10. And for the threshold, 0.5 volt is set for this circuit breaker. Then we add another load to the grid side and after the circuit breaker. So the real power can be anything, it's up to you. It can be, 80k, 100k, and the rated voltage set to 380. And for parameterization, it is specified by the rated power. For the grid side measurement, just copy and paste from the inverter. It's so easy and straightforward. because it's the same setup there. Now it's time to add the transformer to the grid side. Let's set it to the 500, the rated apparent power of the transformer. Set it to 500,000 volt ampere. And the frequency can be 60 or 50, it depends on your design. And WYE with floating neutral, the winding one connection type. And the primary rated voltage, 25,000 volt. And the winding two connection type, they set it to the delta 1 o'clock. And the secondary rated voltage, 380 volt. So the core type should be set to 3-phase 5-limb type transformer. So for the grid simulation, we are going to add a voltage source, 3-phase 1, and with the rated voltage, phase to phase 25,000 voltage, and then set the phase shift, let's add it to 0 degree. Then for the frequency 50 or 60 should be set, and also other parameters, short circuit power level and source X over R ratio can be set to 7. Then just like the other parameters, connecting to the electrical reference. Then for our circuit breaker, to command the circuit breaker, step block is going to be set and connected to the circuit breaker. The timing of this step is up to you. It can be 0.2, 0.3, it depends on your choices. Here you can see the old components of our power circuit design as it is shown in this video. The measurement part and the control system will be shown in a separate video.